Okay, so hi everyone, welcome to today's talk in the IARCS verification seminar series. We are happy to have Subodh Sharma as the speaker for today. Subodh is a faculty member in the computer science department at IIT Delhi. He works primarily in the area of software engineering and formal methods. In fact, a variety of topics within that: static and dynamic analysis, model checking, system security, privacy, blockchains. So today he will be telling us about partial orders and symmetries in message passing concurrency. Yeah, Subodh, so over to you, Subodh.
Yeah, thanks, Madhukar, for the introduction. So like Madhukar said, I'll be talking about some of our past work that we've been doing for quite some time now on using partial orders and symmetries in analyzing message passing applications in particular, and creating practical verification tools. So this is, of course, work done with quite a few collaborators, and I'll have an acknowledgement slide towards the end of my talk. So let me very quickly motivate why message passing systems, why there's a need to analyze message passing. Well, they find heavy use in many applications, starting from scientific computing, client server, peer-to-peer, and consensus protocol implementations. And if you see, most of the applications that run on supercomputers or high performance compute clusters today are running some form of a message passing system. In fact, it comes as no surprise that many languages also support message passing primitives, such as Go, Erlang, Scala. And in fact, there are APIs such as message passing interface with a short form MPI, which provide bindings for languages such as C and Fortran. In fact, it would not be going overboard if I were to say that MPI is perhaps the lingua franca of programming high performance computers. Many applications that are run in today's HPC systems is programmed on MPI or some other message passing system. So one typical trait of these systems is that there's large computation code, which is often interleaved with communication code. And if the computation and communication is not well synchronized, then you may be seeing a lot of issues such as silent data corruption, communication races leading to deadlocks, and so on and so forth. And many of these, properties, in fact, many of these features, if you want to find in programs, you would cast them as reachability properties. And it has been, rather unsurprisingly shown way back in 1983 that reachability is undecidable for such communicating sequential processes, even when they are FSM operating on FIFO buffers. Now, a traditional way to model message passing programs is through the use of partial orders. So in theoretical communities, it's a well-established tradition to use partial orders to capture concurrency. However, their use in constructing practical verifiers has been rather rare. In fact, some of our works in this domain have been the early works. Just to establish some of these terms, that there is no ambiguity, we will talk about soundness and completeness of our verifiers. By soundness, we would mean that the deductive system would be whatever formula that is being proven by our deductive system is indeed valid, while complete would say that the completeness of a decision procedure would mean that all valid formula would be proven by the deductive system. So with this out of the way, let me situate our work in... Is there a question? Okay. So let me situate our work in the larger landscape where people have been working on analyzing message passing systems. So there has been some very remarkable work done in testing where the idea was, given a program run, could you monitor the program run while the process is under execution or while the program is under execution? Of course, it would be very quick, but then it has coverage issues. And then the idea was to then move towards symbolic simulation techniques, where could you reason about a program by symbolically executing the program, thereby addressing the coverage issues. But then there were other issues such as precision and the fact that many a times these programs would work on inputs which were extremely large. For example, scientific computing codes or applications in particular would be working with matrices with dimensions 4,000 by 4,000. Now, to treat all of these complex data structures as symbolic can bring, the most powerful symbolic analyzers down on their knees. And of course, with symbolic simulation techniques, you would also have issues in modeling the environment. So, for example, if you're working with a system offering buffer storage, then you would also have to model how this buffer storage is laid out. So basically, you'll have to model memory, you would have to model system calls, and so on and so forth. And then you have this traditional explicit state model checking, where on some formalism that captures this concurrency, under that formalism, you have some notion of state, you enumerate all the possible states and examine them one by one. And so all of these techniques come with their own sets of problems, but with also their strengths. And we wanted to come up with a technique where we could draw the strength of these spaces. So dynamic symbolic verification seemed natural to us. You run a program idly, get it execution in the form of a sequence of events. Idea is to then generalize from the sequence of event to capture all the possible schedules that one could construct from the events observed in the run and reason about them symbolically. And then you essentially, in an explicit state model checking style, rerun the program, figure out alternate trace that falls in a different equivalence class. What you get in turn is that your dynamic symbolic verification technique can be quickly made sound and complete, although with respect to a fixed input, and would be relatively more scalable. So let me now get into the heart of my talk today, is to define the shape of the programs that I would be verifying, right? So I have shown on the left side of the slide a very simple programming language using which I'll program my processes. So it allows simple assignments. The expression grammar is left unspecified. You can think of any standard expression grammar. Of course, if then else's are also allowed. I have not noted in the in this language, but you can very well assume that. You have send and receive calls, which are essentially asynchronous calls, which means once issued from processes, the control immediately comes back to the process. So essentially, once you issue the call gets registered into the message passing runtime, and the control is returned back to the issuing process. So if I look at the arguments of these calls, PID in the case of send is the destination process to which the send is targeted. X is the data payload, right? So it could be it's some typed variable. And H is a handle which uniquely identifies this non-blocking request in the runtime, right? So similarly, you could understand receive. The only difference in receive is that your PID argument could very well take star as an input, which essentially means that it's a postbox receive. It can receive messages from any sender who's targeting this particular receiver process. And then we have this blocking wait call, which takes in an argument, this handle H. Now, this handle H uniquely identifies a non-blocking request. So wait would block unless the associated non-blocking request associated in terms of this handle H has finished its execution. Now, what does finish essentially mean, or complete mean? So in the case of send, under synchronous semantics, so long as the data payload is not copied out of the sender process's address space and copied into the receiver's address space, the call is not complete. But under asynchronous settings, when the system under which this process is executing offers some system buffering, then the semantics become local. So send would complete as soon as the data payload is copied out from the sender's address space into the system buffer. So wait would unlock.
Question? Can I ask a question?
Yes, please. Absolutely.
So the handle it's how practical is it to expect a programmer to introduce these unique handles in a program, or is there some mechanism which automatically generates these handles?
No. They are specified by the users. You could imagine an array of handles and start assigning, the array entries as unique handle objects.
Okay, so there is some uniform way by which you can.
Absolutely. Right.
Okay.
Yeah. So when you specify this H as an input here, this is actually an output variable. So you provide the typed variable or structure here, and this gets populated by the runtime.
Okay, thank you.
Yeah. And then finally, you have these barrier calls, which are collective calls, which means all processes have to invoke these instructions. And in fact, MPI in particular provides a rich set of collective calls. In fact, if I were to talk about the communication primitives that MPI standard provides, it's well over 300. It's a fairly rich standard. So in my language, I'll be considering only barrier as a representative of all collective calls, and the combinations of send, receive, wait, and barrier is reasonably good enough to model most of the collective calls and other point-to-point communication primitives. So the semantics of barrier is that if one call has issued a barrier, then it will be stuck in that barrier until unless every process in the communication topology has issued that specific barrier. So with these as the call semantics, let me come to the aspect of where is partial orders used. So the partial order is used in tying up events coming from a single process. What we need is the ability to figure out when can a call match before other calls or after other calls. And therein, we came up with this partial ordering relation called matches before, where we specified, by reading the standard, we specified the rules using which we can identify these dependencies. When can a call match before other calls? So let me take a few examples. From a given process, if there are two sends issued targeting the same destination process, then they must match in the program order. So that's rule number 2, shown in the slides. Similarly, there is an ordering relationship between the send and its subsequent wait, rather associated wait. So, the send call must complete before wait can unblock. So here I am changing the semantics slightly from matches to completeness, but this change in semantics is subtle. And if there is interest, I can talk about it after my talk. And then, quite straightforwardly, if you have a blocking call such as wait, then there's a natural matches before ordering with any operation that is coming immediately after this blocking operation. So that's rule number 3. So we construct this matches before relation, encode process specific events dependencies through this relation. And this is
sorry, the question.
Yes, go ahead.
On the previous, yeah. So the matches relation is with respect to one execution, is it?
The matches before relation is irrespective of the execution. This is driven by the semantics. So this matches before would hold true no matter what execution you come up with.
No. So what is it matching? I mean, what is the domain of the relation?
So the domain of the relation is basically the communication primitives seen in the execution trace.
Okay, so it's with
So
respect to
while it may look that it is specific to the execution trace, they are general. So even if you change the schedule, the send will always match before its associated wait. Or two sends from the same process targeting the same destination will always match in program order, no matter which schedule you explore.
Mhm. So this is like a happens before kind of relation, is it?
Yeah, but it's not execution specific or trace specific.
Because of the unique handles, basically, right? Because
Well, handles only appear in some of the rules. So for example, if you have two sends or two receives, handles have no role to play.
yeah, so
But
therefore
this is essentially driven from the semantics as espoused in the standard. Does that answer your question?
So
Okay.
intuitively, what is matches before try to capture? Maybe I'm missing that.
So matches before is just trying to identify under, so if I have been provided a sequence of events from a particular process, which events would match first before others? So some dependency relation among the events from the same process in terms of their matching guarantee. So I could have imagined two sends. The first send could be targeting process I, and the subsequent send is targeting process J. Now, these are two asynchronous sends, and if there is no intervening wait in between them, then the standard does not impose any guarantee in the order in which they match. It is possible that the later issued send may match first in terms of global time.
So what do you mean by match?
Matching, yes. So this essentially comes to the heart of the this discussion. So matching essentially says that if I have two calls, so for example, in the for send, matching would be whether in the runtime has registered or found a matching partner alive. So for a send, it would be whether receive has been issued by the matching process or not, or there's a matching receive alive in the runtime or not. For wait, you don't require matching because wait has local completion semantics. But for barrier matching would be until unless every process in the communication topology has invoked this call.
Okay, so it's basically like some events which enable this. I mean, what events is it dependent on to make it enabled?
Subodh, is it okay to understand this as given a program, you can think of the set of all events that could be part of any execution, and this ordering fixes the ordering between those events, and then no matter what execution you have, you can extract a matches before for that execution. But the order is not dependent on the execution. That's what you mean, right? It's only dependent on the program and the set of events of the program.
Absolutely, absolutely. And to come to Deepak's question, it's truly not an enabling thing because the call has already been issued. It may be just sitting in runtime, and when an associated wait is seen later in the program, it would be blocked until a matching call has been issued by some other process. And once the match status has been set, then the matching calls may move towards completion. So the completion semantics are slightly different from matches.
Okay.
Right?
Okay, thanks.
Yeah. Okay, so that was the important part. Let me skip the formal MPI semantics. It's not important at this point in time. The only assumptions that I'm going to make is I'm going to work with finite state machines. So each process is an FSM performing deterministic computation. Although this is not a showstopper, we can deal with non-deterministic computation as well. But just for simplicity of presentation, we'll assume deterministic computation are per process system buffers are going to be FIFO, and under which we model two categories of it. So synchronous communication, which is also called rendezvous in the literature, which means that for send to successfully match a receive, the matching semantics align with the completion semantics, which means the sent data payload has to be copied out from the sender's address space and copied into the receiver's address space. Right, so that's the synchronous semantics. While for under asynchronous semantics, when you have non-zero buffering, system buffering available, then the send semantics essentially become local. So the send would complete and therefore match as soon as the send data payload is copied out from the user's sender's address space into the system buffer. So that's all. And of course, the programs are assumed to have finite control, working with finite data domains. So under these assumptions, we show some theoretical results. So here is a simple, before I get to them, here is a simple message passing interface program, an MPI program. You have 4 processes, P1 to P4. P2 to P4 are sender processes. Right? So let me use my mouse pointer to emphasize. I hope you are able to see my mouse pointer. Okay, so each of these sender processes, process P2 to process P4, they are sending one message to process P1 with certain data payload. That is not important. So if you look at process P1 posts a sequence of wildcard receives. So this wildcard is shown by this star, right? So R1 is post one wildcard receive followed by R2, R3, and R5. Okay, so there's a typo, it should have been R4, but yeah. Now note that these receives are essentially point to point, I mean, they are functions, so they can match only one send call. And the send calls from sender processes, they are all racing with each other to match these receive calls posted by the receiver. Now, if you look at this receive at R1, depending on which send it matches with, determines the subsequent control flow of the receiver process P1, right? Because that control flow is dependent on the value received in this variable X. So these kind of programs are termed as multipath programs, where the communicated data determines the control flow of the receiver process. And this leads to non-determinism in control. So non-determinism in scheduling, in matching of events, leads to non-determinism in control flow. So even without this complexity of multipath programs where the communicated data does not affect the communication flow of, or rather the control flow of the receiver process, which we call as single path programs, we show that the deadlock discovery problem is NP complete both under finite and infinite buffering models. So even under the simplest case, the problem is intractable. And for multipath programs, the situation is seemingly under control if we make certain assumptions on the data domains and the number and the kind of equalities that appear in if-then-else expressions. But I'll be happy to talk about that after the, yeah.
Subodh, one question. The primitives in the language we are looking at doesn't have synchronous send and receive directly, right?
Yeah.
The send and receive.
Yes, they don't have synchronous sends and receives, but what I can do is I can juxtapose send with a wait without any intervening call, and this essentially converts to a synchronous send.
Okay.
Well, actually, it does not, because I have to specify that the system buffer is essentially 0. So even with send and wait juxtaposed, if there is system buffering, you cannot truly model synchronous semantics. You would have to provide a command line argument that suggests that you're working with 0 system buffering. And then this juxtaposition would be sufficient.
So wait H means you're waiting for H to have been sent.
Yeah, so you're waiting for the communication call uniquely identified by this handle H to have completed.
Okay.
Yeah.
Also in that program you showed, is P3 meant to send 20 or?
No, so yeah, I mean, the reason why I put 10, so that's not a typo, okay. Is to show that, well, many processes could flow through just a single control flow path, can take the single control flow path in the receiver process.
Mm.
But that's okay.
Subodh, the wait, one thread could wait on a send or receive done by another thread also, is it?
No,
So this-
wait. So wait only waits on. So these are all process specific events, right? So wait would essentially wait on a prior call made from the very same process.
Okay.
Yeah.
So we can't pass the request handle through a message or something.
Right. So you can view them as single program multiple data programs, right? So SPMD. So basically, each process is executing in its own memory. It's completed distributed memory programs. So this wait would have process level semantics here. Although that was a great question, because some modern languages like Go allow such things. You could pass in channels, and those channels could be used by other Go threads doing some fancy thing. So that complicates the reasoning. All right. So that was what I wanted to say about the complexity of verification. So what did we do? So this is what is our technique. We start with simple, or rather MPI programs. We statically instrument them because the concurrency here is reasonable, because it uses well-defined API calls. So we instrument all the communication primitives as well as the if then else blocks which are affected by communication. And then we craft a deterministic scheduler that could orchestrate different schedules of the program under run. So we take an input I, run this instrumented program under the control of our deterministic scheduler, and produce a sequence of events. And for us, each event is a matching send and receive, or a wait, or a collection of barriers. So that's the formal definition of sequence. I have not included a formal definition of what an event is in my trace. I have not included in the slides, but I've articulated it. So it's essentially a sequence of matches between send and receive, or a wait call, or a collection of matching barriers. So that's the trace that I get. Additionally, I take a property that I would like to verify as an input, and I feed it to a VC generator or an encoder which generates verification conditions. And the goal of this verification condition generator is to give me a formula that not only encodes the matches before relation, but also tells the underlying decision procedure, where I'll feed this formula later on, how to construct alternate schedules which are admissible under the message passing standard with which we are working. And in our case, it was NPI. So the formula that it produces is this phi, which has got these three components: PO, exec, and prop. So negated prop is something that we have already taken as an input. Phi exec is a formula that encodes how does alternate schedules can be constructed from the set of events that was observed in tau by matching it differently. So how can I match a particular non-deterministic receive with a different send so that I do not violate the data or control flow decisions made in the program, or do not violate the guarantees imposed by the message passing standard. For example, the matches before guarantees. So that is included in phi exec. And once we have this formula phi, we feed it into some SAT or SMT solver. In our case, propositional encoding sufficed for communication deadlocks, and a satisfying model would essentially mean that there exists an alternate matching schedule of these events, which leads to a deadlock, communication deadlock. We show that our encoding is sound and complete. Yes.
Yeah, sorry. So maybe I missed that, but what is the deadlocking trace?
So a deadlocking trace is a trace where, so I did not specify it. That's thanks for asking this question. A deadlocking trace is a trace wherein some communication primitive has not found a match. Because under MPI, even if one process is unable to make a progress, it will lead to a system-wide deadlock, because every process at the end of its execution has to call a collective barrier. So if one process is stuck and not making progress, eventually it will never hit that final barrier and will lead to a system-wide deadlock.
Okay, and you don't assume any fairness in scheduling?
No, we don't.
Okay. Okay.
So in the case, if the formula turns out to be unsatisfiable, it means that all the schedules that one could come up from the events observed in trace tau do not lead to property violation. So the idea now is to see and investigate whether I can traverse some alternate control flow path in the program, in some process of the program, so that I see at least one new event different from the set of events seen in trace tau, the prior trace. And this essentially involves changing this formula phi by taking negation of phi prop away. And so I will not get into the details, but essentially this involves another SMT query, a SAT SMT query. And if it turns out you have a satisfying model, that means decidedly or provably you have found an alternate path in a program such that there will be a different control flow decision exercised. So what we do is we take that partial model, feed it into the deterministic scheduler, and generate a new trace tau prime, which provably falls in a different equivalence class. And for me, equivalence class is the set of all those schedules which exercise the same control decisions, right? The termination of, so this loop will iterate until unless there are no more paths to be found, in which case we have model checked all the behaviors that could manifest on a given input I for this program P. And and if it has terminated without any property violation, then the property is verified under this very input. The termination is guaranteed because you have finite number of control decisions. We additionally show our encoding to be sound and complete. That means there is a deadlocking trace if and only if there is a satisfying assignment to this formula phi.
So the trace you look at is kind of complete in some way. I mean, what if I just, what kind of a trace do you consider? It has to kind of reach some, or you just take any finite execution and just terminate at some point and you look.
Right. So if you look at the language that I described here, loops are conspicuously absent here. So I am assuming that all the executions of the program are terminating in nature.
Okay.
Right. And this is usually, so let me also just make a quick observation here. That's usually the case with most scientific computing applications, which are convergent in nature. So, yeah.
Subodh, is this so you also, your deadlock detection also works with sound and complete with unbounded buffers, is that right? You don't need bounded.
So no, it works with zero buffers and as well as infinite buffers. With K buffers, the complexity, the problem gets into a higher complexity class.
No, but you never need, you only need buffers, no? Because you just have finite straight line programs.
That's true. We have finite straight line programs, but buffers play an interesting role in changing our matches before semantics. So, so under zero and infinite buffering, I don't have a dynamic update on my matches before. But with some unknown but bounded buffering K, I don't know how my matches before relation would change, right? So then the problem becomes slightly more complex. But with 0 and infinity, the problem is very simple. So I'll tell you what happens under infinite buffering. Under infinite buffering, every send call that's issued immediately completes, which means its associated wait calls become no ops. And therefore, this third rule vanishes. Because waits do not exist, in a sense, notionally, you could very well remove this wait to its this matches before relation of a wait and the subsequent operation. So if that makes sense, then I can go ahead. Let me not get into
just a thought. So I mean, these can also be represented by message sequence charts, right?
Very well. Yeah, they can be represented
essentially a message sequence chart. Your execution is a message sequence chart, and deadlock is basically some unfinished, some send that has not yet been received, or some
that's right.
barrier that doesn't have all the.
Or it could also be a cycle. So deadlock also involves these cyclic dependencies, communication dependencies that send. So you could have two processes engaged in sends to each other under synchronous semantics. So process 1 sends to process P2 and blocks because it's synchronous. And process P2 sends to process P1 and blocks. And they're expecting the receives to be invoked, but none are to be seen. So this is a head-to-head deadlock, a classic head-to-head deadlock. Yeah.
So how do you detect, so you have a formula which detects a deadlock, is it? I mean, maybe.
That's right. So this formula phi essentially, so if I can get into my propositional encoding, although time will not permit, but let me very quickly.
Let's not look at the logic, but I mean, just intuitively, what is the condition that you check for deadlock? I mean, I give you.
So basically, I check that I am at a state in my execution where I cannot legitimately extend this execution with the events that are alive in the system and not yet matched. And that is a deadlock.
Okay, and you assume that each thread has kind of is stuck. I mean, the execution you look at, I mean, like the 2 send thing that you mentioned, right?
Yeah.
I mean, there may be various other things that it could do after those, but I mean, you need to know that you have a kind of complete execution. It's not a partial execution that you have just cut off.
That's true. That's true. So what I would need, so basically if the deadlock manifests right in the first run of the program, this VC encoding doesn't need to engage at all. So if the deadlock is manifested right in the first run, then there is no need of this fancy machinery.
So how do you know that the first run is finished?
Because you're running under this deterministic scheduler, right? So it's orchestrating the run. It's orchestrating the run. And if it is already stuck, it has shown that the deadlock has happened because it cannot find an alternate, an event alive in the system to further the trace. I mean, it cannot extend the execution at all. So the deterministic scheduler is mimicking the runtime. So if there is no non-determinism in the execution, then the first run of the program will hit a deadlock. Your deterministic scheduler and all of this VC encoder and SMT solver will come into picture only when you have non-determinism in the code, where you had a successful first run, but there is an alternate matching of events seen in this run, which can potentially lead to a deadlock.
Okay.
So you have actually witnessed the entire first run successfully. Okay. Yeah. Okay, so let me not get into this propositional encoding, but quickly talk about the results. So we compared with two stateless model checkers. So ASLN was a state-of-the-art model checker for NPI programs. And one complete symbolic verifier, civil. And So if you could see, I'll draw your attention to these colored boxes, and Hermes was our tool. And we saw that for multi-path programs, ISP was just timing out for some representative scientific computing benchmarks like matrix multiplication, Monte Carlo simulations, 2D diffusion, integration, etc., etc. AceLen was using some partial order reduction techniques, was able to fare much better, yet it was timing out as soon as we bumped up the number of processes on which we would want to verify. Civil, which was a full-blown symbolic verification tool, would take awfully a lot of time. And Hermes was doing fairly well on very few runs, right? So the number of program runs it had to do was very small. And much of the analysis was shipped to the symbolic analysis, right? So under the SAT encoding, the SAT solver essentially enumerated the abstract schedules and reasoned about them. So in summary, we saw orders of magnitude speed up than explicit state model checkers and full symbolic verifiers. So dynamic symbolic verification had some merit to it. And very quickly, in fact, we also realized that these encodings were not just specific to MPI programs. It turned out that there are almost 14,000 commits on GitHub that we identified, where there were discussions relating to weight notified deadlocks in Java 8 multi-threaded Apache libraries. Now, this is not distributed memory applications. These are shared memory applications, but they have these communication deadlocks appearing because of weight notify signals. And if one thread is sends a notify signal and the weight other thread has not already been waiting on it, then the signals could be missed, leading to these communication deadlocks. Similar encodings that I just spoke about were applicable in that setting as well. All right, so I am left with 15 minutes. So maybe I'll try to wrap this talk up in 10 minutes. So as such, we were doing fairly well, but upon deeper investigation, we realized that our SAT solvers were stuck in exploring symmetric runs of a program when the programs were verified on larger number of processes. And so we realized the need that, well, I think we could speed up the verification process if somehow the solvers are made aware of these symmetries in programs. And rather unsurprisingly, many message passing programs are developed with inherent with symmetry in mind. So many processes are doing the same thing. When I say doing the same thing, I mean that communicationally, the communication skeleton of the program or processes is very similar. Computationally, also they are very similar, except that they may be working on different data. So we started working on this, how could we break these symmetries in the solver once we have encoded the problem as a SAT problem? How can we instruct the scheduler not to explore symmetric runs of the program? Therein we realized that these symmetries are not global. So there are tools that are already in the domain, such as break ID and shatter, which automatically discover symmetries in program if you have encoded these programs as SAT formulae. But unfortunately, shatter and break ID kind of tools would not work in our setting because the symmetries in message passing programs may not always be global. They may appear localized in some snippets of the code. So what we did was we, again, clubbed in. So if you remember this tool flow, we started with our deterministic scheduler, took out the trace, which is a sequence of events, and events constitute matching sends and receives, waits, and collection of matching barriers. Once we have that trace, we convert that trace into a program graph. We consider that trace as a program definition for us. And we construct a program graph as set of nodes and edges, where, of course, communication calls constitute nodes. And the edges are comprised of events involved in matches before relationship. So for example, if a send from process P0 and a barrier from process P0 are in a matches before relation, then this would constitute an edge from send to barrier node in my program graph. Additionally, there would be a bidirectional edge between matching events. So for example, this send to P1 could match this wildcard receive from process P1. So there is a bidirectional edge that is added into our program graph. Once we have designed these program graphs, then we ended up identifying epochs, which are essentially strongly connected components over this program graph. These communication epochs essentially defined for us regions within which every call issued would find its match. And this was important because now our symmetry detection was localized within these epochs or strongly connected components. So that was the part that dealt with identifying local symmetries. Once the local symmetries were detected, so basically regions in which you have to do local symmetry detection. How do you do that? You do that by identifying automorphisms, which are essentially bijections, structure preserving bijections, in fact, edge preserving bijections of the form that if C1, C2, if there's an edge between two nodes C1, C2, if and only if under that automorphism pi of C1, pi of C2 is also an edge in your program graph. So pi is just a function that would map these edges in a way which preserves the structure of your program graph. We show in our lemma that pi preserves these matches before relation, as well as deadlocks, if any, constructed from that particular set of events seen in that trace tau. In fact, intuitively, automorphism is essentially defining an equivalence class partitioning for you. So once you have figured out these automorphisms, the way to figure out these automorphisms is essentially a collection of automorphisms for a particular graph constitutes a group. And this group could be exponentially large in the size of the graph. So typically what people do is limit themselves to working with only generators of the group. So if your graph is of size n nodes, then what they have to do is that they identify n-1 generators, and that suffices to populate all the possible automorphisms. Right. So once you have constructed these automorphisms, then the idea is how do you instruct the SAT solver to identify these symmetries and break these symmetries. What it means essentially is telling the scheduler not to explore symmetric runs. And the way it is done is by providing these symmetry breaking predicates. This has been a well-studied notion in the planning and AI literature space. The idea is you specify some lexicographic ordering between the behaviors or the schedules that fall in a single equivalence class as specified by a single automorphism, right? And there are many encodings to do that. In fact, I have shown you one encoding here, which I'm not going to go into detail. In literature, these encodings are called AND CSE encodings. So basically, these are simple AND constraints, and the encoding would make sure that common sub-expressions are all eliminated. So it's AND CSE encoding. So once you have an AND CSE encoding, I would just emphasize the last rule in this AND CSE encoding, which defines a lexicographic ordering between tau and pi of tau. So basically, I have lifted the notion of pi from pair of events or pair of nodes all the way to traces altogether, which is shown by the square brackets and the symbol in between. So you define these lexicographic orderings, and pi essentially is being enumerated from the set B, which is generated by the generators of the group, right? So it's basically a collection of generators of the group. So as such, our dynamic symbolic verifier was already giving us orders of magnitude speed up over explicit state model checkers and full symbolic verifiers. With symmetries, we saw exponential savings over our own dynamic symbolic verifier. So I'll not take you through the table on the left, but here are some representative figures on some representative benchmarks like 2D diffusion solver, where our tool with symmetry breaking predicates, symmetry breaking like Simian, that's the tool name, showed exponential savings over our optimized Hermes tool, which was based on Mauperot. And we also have this figure which shows that, well, we had to spend some more time in discovering these communication epochs and computing these automorphisms. But we realized that because our our program graphs were usually very small, the analysis time spent in identifying these automorphisms and epochs was rather small. It was less than 10% of the total analysis time. And so this was the summary, and I think this was my last talk. So in summary, we provided a dynamic symbolic verification tool and technique, which exploited heavily on how can one encode the dependencies, the matching before dependencies in message passing programs through this partial order relation, which we defined. And then this entire dynamic symbolic verifier essentially relied on that. And then to augment the efficiency of that tool, we leverage the inherent symmetries. So with that, I will end my talk. And if there are any more questions, I'll be happy to take. By the way, these are the collaborators with whom this work was accomplished. Thank you.
Yeah, thanks, Subodh, for a wonderful talk. And I think we do have time for a few questions. So.
Yeah.
So in terms of the complexity of the symmetry finding thing, this is linear in
the number of generators, but exponential because automorphism computation itself could be exponential time.
Okay.
Yeah. But we did not see that exponentiality manifesting in our cases because program graphs were fairly small.
Correct. Yeah, you mentioned that
So
the
even with
less than 10%.
Right.
Yeah.
Even with a million events long trace are, these epochs. Once I have identified the epochs were small enough.
Okay.
Having, say, 10 nodes or 100 nodes. So these are smallish graphs of at most 1,000 nodes.
Okay.
So that exponentiality did not manifest here.
Okay.
We use, by the way, off-the-shelf automorphism generator called Bliss.
Okay.
Yeah.
So, Subodh, I had one question.
Yeah, Deepak.
I mean, why do you need to take a execution in this work? I mean, why do you anyway have kind of like essentially straight line or maybe some if branching programs? Can't you just create a formula directly just from the program rather than looking at an execution?
Yeah, we could very well do that, but that so this could very well be clubbed with symbolic verification tools as well. You're right. But because we had already a well-engineered system, and we are building on top of it, so we had already obtained traces. We had applied symmetries to them. But the problem with full symbolic verification tools is how do you deal with data? So if your input data is these big matrices, then you have to have some way to sort of abstract them out. Otherwise, symmetry breaking or not, your tools will not scale.
I see. So the input data is, I mean, that plays a role in the...
Huge role, yeah. So especially in scientific computing applications, which are working on fairly large inputs, this can be a problem.
Okay, but I mean, in principle, it's possible to generate a formula that covers, I mean, that just basically directly translates it.
Absolutely. Absolutely. Yeah.
So basically, using your tool, you were able to find deadlock issues that other tools kind of timed out on, is it? Or they were not able to find at all? I mean,
so we were able to find deadlocks, but not in production quality systems. These were deadlocks which are already known. So the problem is that many of these tools, so the applications, so yeah, that's actually a good question. So the benchmarks where we showed the efficacy of these tools is in terms of whether or not they could verify the program to show absence of communication deadlocks quickly. Because many benchmarks did not have deadlocks. We tried to seed them. Of course, then deadlocks could be caught very quickly.
Okay, so if there are no deadlocks, you are able to prove that by just
by using symmetry breaking constraints very quickly.
You have to basically, examine a kind of representative set of execution traces.
Correct. For a single input, because we are sound and complete, we run through this entire space very quickly using symmetry breaking predicates and come back. So for example, Hermes and other tools would time out. And just because all of these tools are trying to look for schedules under which it can possibly deadlock. So in many benchmarks which were not deadlocking, the tools actually ran out of time. In fact, we tried to seed some benchmarks, and in which case the deadlocks were caught fairly quickly by all the tools. Reason being, I've realized this creating benchmarks with seeding bugs itself is a hard problem. How do you seed bugs so that it's hard to catch? There has been some work in this space by Subodh Roy from ITK.
No, but even if you could find a proof, I think that's good, right? I mean, if you can find
that's good. Yeah. In fact, there are some very interesting directions for this work. One is, could you amplify the results one has obtained for a single input to a class of inputs? Because oftentimes communicated data affecting control flow is not there unless you're dealing with some sort of a load balancing application. So message passing applications, input data rarely affects the control flow, or the communicated data rarely affects the control flow. If that is the case, then one should be ideally able to amplify their results seen on a single trace, a single input, to a much larger set of input domain. Second is parametric analysis. Could you actually, so if you see in much of our analysis, we fixed the number of processes. So we made quite a few things symbolic, but things that were concrete for us were the input data and the number of processes, even under symmetry breaking predicates. Now, the question is, could you identify some cutoff k such that you model check until that k, and then say that if you have model check until k, you have model check for all processes. So this kind of analysis would then vanish, that you have to analyze for 8 processes, then 16 processes, then 32 processes, then 64, and so on and so forth. Because most of these message passing programs are run on clusters with 500,000 nodes, run on million processes, right? So ideally, one would want to do this parametric analysis in the number of processes. And I think that is doable because this is not the wild west form of concurrency. Here, the concurrency is way more structured. So one could have such results in this space.
So I mean that.
You mentioned that there is a lot of variety of barriers or synchronization. So how well does this reducing it to one single barrier generalize to all of them? Like, are there some barriers which are not exposable using this?
Sorry, I didn't understand the question. Could you?
Are there some operations in the MPI which won't be easily expressible using these primitives? Like a barrier with much more complex semantics.
Indeed. So there are primitives, communication primitives, which so basically these calls are sufficient to model most primitives, but not all. So for example, there is a scatter operation. There is one node that gets some data and then broadcasts it to a collection of processes in a certain way, right? So that scattering could be essentially done through point-to-point communications followed by barrier, right? And on the recipient side, it could be modeled as a sequence of receives followed by a barrier. So in my knowledge, in applications that we saw, many, in fact, benchmarks were not, were in fact using primitives which were way richer than what we had specified, but we had to essentially model them as a collection of send and receives. But I'm pretty sure if there are 300 primitives, there would be some primitives which could not be modeled by this 4. But this largely is representative of a good set of MPI calls, I would say.
Okay.
Yeah. The only thing is that if you don't explicitly model those collective calls in your verifiers, then it is quite possible that for some of those collective calls, you may have to involve a whole bunch of point-to-point communication calls such as send and receive, which may increase the verification complexity, right? So if you have directly encoded the semantics of some collective call as opposed to modeling it as a bunch of send and receive. So if you have a communication topology of say 1 million processes and you have a broadcast modeled as million sends, then you have increased the verification complexity, right? So for efficiency purposes, you would want to perhaps model collectives as such.
Okay.
Yeah. Okay. So if there are no further questions, yeah, let's thank Subodh once again. Maybe we can unmute and.
Thank you.
Yeah. Thanks a lot, Subodh, for the talk.
Yeah. Thanks for the opportunity to give a talk here. Thanks. And I enjoyed the questions. Great questions.